Welcome to iLectureOnline, and here's a very practical example of how we deal with impulse in the real world. Let's say we have an old car that will only collapse 40 centimeters so when hitting a brick wall. So when a car hits a wall or a cement post or another car coming the other direction and there's this massive impact, the front of the car will crumple a certain distance. And let's say old cars were built very, very strong. They didn't collapse very much. So let's say that when an old car hits a wall, it only collapses 40 centimeters in the front when going 90 kilometers per hour, which is about freeway speed, about 55 miles per hour. A newer car will collapse 100 centimeters, so much more the front end will collapse under the same conditions. So what is the difference in the force acting on an 80 kilogram driver? So let's try to figure this out. So when an older car smashes into a brick wall, the front end will collapse a distance of about 40 centimeters. So how long did it take for that car to be crumpled up? If this was the original front end of the car and it collapsed 40 centimeters, how long did it take to cover that distance? And so the average speed during that period of time when the car was crumbling would be the speed would be halfway between what it was when it started hitting the wall and zero when the car came to a complete stop. So the velocity average, and let me put some wheels on there. So there we go. So the velocity average is equal to V initial plus V final divided by 2. So that would be 90 kilometers per hour plus 0 divided by 2, which is 45 kilometers per hour. And if we convert that to meters per second, we have to then say, okay, we'll have to convert from kilometers to meters. So with meters there, kilometers there, 1 kilometer is 1,000 meters. And then converting with hours, we need to go to seconds. And this is hours. 1 hour is 3,600 seconds. And when we divide that, I remember correctly, it would be 12.5 meters per second. So the average velocity during the impact is 12.5 meters per second. And if the driver covers a distance of 40 centimeters, how long did it take for that collision to actually take place? So we could say that the velocity is equal to distance over time, which means that time is equal to distance divided by velocity. So 0.4 meters divided by 12.5 meters per second will give us the time that that particular collision lasted. So that would be 0.4 divided by 12.5, and that's 0.032 seconds, which is 32 milliseconds. So in a front-end collision with an old car that only collapses 40 centimeters, the collision lasts about 0.032 seconds. Remember impulse. The definition of impulse is equal to the force times the amount of time that the force is acted upon. And since the impulse is also defined as the change in momentum, the delta P, which is equal to m times delta, that's a kind of a weird looking delta sign here. Let me correct that. So delta V. You can see then that the impulse of the collision will cause the car to slow down. The change of momentum will not change, right? The change of momentum is still going from maximum velocity to 0, but it will do that over a short amount of time. Means short amount of time for the same impulse means that we have a greater force. So if the time is less, the force must then be greater to give you the same impulse, the same change in momentum. How much time would it take for a newer car that has a much greater distance to collapse? So for example, newer cars are built so that the whole front end collapses. The driver and the passenger are still safe inside the compartment, but the whole front end collapses, giving it more time to slow down. Meaning the delta T will be not as small. That means the force will not be as great. So if we then use this very same equation, we have the same average velocity from 90 kilometers per hour to 0, but the collapse will be greater distance. So time for the second car, let's call this for the first car, is equal to distance over velocity. In this case, it's a whole meter divided by 12.5 meters per second. And so that would be 2.5 times as great, so times 2.5, and we get 0.080 seconds. 2.5 times as much time means 2.5 times less force acting on the driver. Now, remember, the drivers and the passengers, they're strapped down with their seat belts, so when they get into a front-end collision, the seat belt stops them, but the force that the seat belt will push on the will use to push on the passenger and the driver with will be much smaller, and therefore not as much injury, not as much pain in the collision. All right, so what is the difference in force on an 80-kilogram driver? So how much force is required to change the momentum of the driver? So here we can first go to this equation and figure out the change in momentum of the driver. So the impulse, which is equal to the change in momentum, which is equal to m times delta v, is equal to the mass of the driver, which is 80 kilograms. And how much did the velocity change? Well, the average velocity was 12 meters per second, but at 90 kilometers per hour, the speed is 25 meters per second. So we can plug in 25 meters per second. That is the change in the velocity, because the driver went from 25 meters per second to 0. So 25 times that would be 6. That would be 2,000 kilograms meters per second. So that's the impulse, which is also the change in momentum. If we now want to figure out how much force is involved in this collision, the force on the driver slowing him down, we use the other equation. Impulse is equal to force times the change in time. So we can solve this equation for force. The force is equal to the impulse divided by the amount of time that the collision took. Impulse being 2,000 kilograms meters per second. And the time, well, let's do it for the first car, 0.032 seconds. 0.032 seconds. That would be 2,000 divided by 0.032 equals, that would be 62,500 newtons of force. If we do the same thing for the newer car, the impulse being the same, force times delta t, solving this for F is equal to I divided by delta t, and plugging those numbers in, we get 2,000 kilograms meters per second divided by, in this case it took a whole 80 milliseconds. It may not seem like a lot. I guess I should put seconds down here, but that's an additional 48 milliseconds. And if we do the very same calculation, but with a different time, we only have a force of 25,000 newtons. So definitely a lot easier on the chest when you hit a brick wall going 90 kilometers per hour. A lot less forces if you drive a newer car that crumples over greater distance, offering a greater amount of time for the car to come to a stop, and therefore, since impulse is force times delta t, a lot less force because it's distributed over a greater amount of time. Okay, a very practical example of how we use impulse and momentum. All right, I want to continue this a little bit. I was just reminded that not a lot of people in certain countries of the world, like the United States, may not realize what 25,000 newtons of force is. So we have a nice little conversion. We know that 1 pound of force is equal to 4.48 newtons. I believe that's the conversion. I might be off by just a little bit, but it's close to that. So let's convert these forces to pounds of force. So multiply this times. We want pounds instead of newtons. So 1 pound, 4.48 newtons. So let's take 62,500 and divide it by 4.48. And that is a force of 13,000, I'll just round it off, 400 pounds of force. That feels like being hit by a sledgehammer, doesn't it? A very big one at that. But if it's only 25,000 newtons, and we get 25,000 divided by 4.48 equals about 5,600 pounds. Well, it may be the difference between a set of broken ribs and coming out of there with just a very bad headache. 5,600 pounds is a lot of force, but the human body, amazingly, is strong enough probably to withhold that, and you probably do not have anything more than just a very sore chest, very sore stomach, maybe a whiplash or something like that, but you'll come out of there in pretty good shape. With this kind of force, you might come out there with a set of broken ribs and so forth. That's the reason why they put an airbag in the car, because that gives you additional protection in, again, increasing the amount of time that the force acts upon you, thus lowering the forces on the overall body. But that gives you a good feel, if you are more familiar with pounds, of what the difference is in a front-end collision like that.